Pepe Vila, and this is a joint work with Boris Köpf, who is also here. And first of all, event-driven programming is so-called right now, and it simply consists on defining responses to user actions, input-output signals, or messages from other processes or programs. And this paradigm has been mostly used by graphical user interfaces and also clients. And in fact, the HTML5 specification itself mandates to use it. But more recently, we have seen that there is an adoption on other environments like server-side application or network programming, and Node.js or Nginx are examples. And the main reason for this is that when well used, event-driven programming provides a very high throughput and a very simple concurrency model for programmers. Each event-driven program have an event loop, and the event loop consists of a FIFO queue and a control process or a control thread. And the idea is that when messages arrive, or events, they are pushed into a queue, and the control process will dispatch them sequentially one by one, following a FIFO policy. And when they are dispatched, they are sent to the specific event handler. So in this work, what we do is show that shared event loops in the Chrome web browser pose a security threat to users. And for this, we exploit two different shared event loops in Chrome. These two are the event loop of the input-output thread of the host process and the event loop of the main thread of the renderers. And for this, we implement three different attacks, namely the page identification attack, where we try to recognize which page is being loaded in the web browser by observing the congestion on the resource. And to give you an idea, in this picture you can see a visualization of this congestion while loading three different web pages. In the X, we have the 5 seconds while we were monitoring the loop, and these peaks represent the congestion. The next attack is an inter-keystroke timing attack, where we try to detect keystrokes performed by a user in a different tab or in a different web page in the same browser. And this is how a keystroke in a specific web page looks like. And finally, the last attack is a covert channel, where two cooperative web pages try to communicate through these event loops. And we communicate even across pages in incognito mode. So this is what we do, but how this can work, or how this works. Here we have a shared event loop with its FIFO queue and the dispatcher, and the idea is very simple. This event loop is shared between an attacker and a victim, and what the attacker will be doing is start posting events. Since the dispatcher is free, it will unqueue it and start processing, and while this happens, the attacker keeps posting tasks into the queue. Now, when the dispatcher finishes, here I will save the timeline of the events. Now the dispatcher continues processing tasks one by one, and at some point, the victim will also post some task. And what happens when the dispatcher starts processing this victim's event is that the event from the attacker has to wait some time in the queue, and this is the fact that we will exploit. So now the attacker can continue posting tasks or events, and at the end we get something like that. And the idea is that the attacker has no information about the victim's messages; he cannot read them, but he has information about the time when his own events were processed. And this is what we call the event delay trace. The attacker can measure the time or the delay between two of its own consecutive tasks. And when he detects a large delay, he can infer that it's probably the loop was busy processing some victim's event. And to give you an idea of how this event loop story fits into the Chrome web browser, here I will try to give you an overview of the Chrome architecture. Chrome is a multiprocess browser, and it has a host process with an event loop, and this host process is the only one with privilege for accessing the external world, or the file system, or the internet. And this event loop will handle events related to network requests, inter-process communication, will dispatch the user actions that enter from the operating system, and will be shared between all the renderers in the web browser. And the renderers will be operating system process as well that contain or host the web content. All the HTML, the JavaScript runs in a specific renderer. So these renderers are sandboxing. They cannot communicate directly with external world, and they can't also communicate between them. But what happens here is that even if the security mechanism of the browser disallow these accesses, a malicious web page running in the browser can interact with the shared event loop in the way that I showed before, and extract information of what the user is doing in a different tab, for instance. And to give you an idea of how easy it is to do this, this is all the JavaScript that we need to obtain an event delay trace for this host process, for this event loop in the host process. Here we have a loop function that, first of all, saved a timestamp. The performance now is simply the JavaScript API for getting a high-resolution timestamp. And the save function will only push this value into a pre-allocated array. And after saving this timestamp, we will perform a network request, which will send an event to the event loop of the host process. The trick here is that by assigning an invalid IP address, the event loop will throw an exception very fast, and then we can catch this exception. And when we catch the exception, we execute the same function again. And in this way, we will be continuously posting events into the queue and saving the timestamp to get the delay trace that we want to obtain. With this simple approach, we obtain a timing resolution of around 500 microseconds. And by timing resolution, I mean that 2 consecutive events will have this delay. And well, in the paper we show some other techniques where we can obtain a resolution of less than 100 microseconds. So we have another important event loop inside the renderers, and these event loops will handle JavaScript execution tasks, resource parsing, layout, calculation, and some rendering operations. And these, well, while ideally each tab in your browser or each web page should be hosted by a single renderer, there are some cases where these renderers are shared. And this happens when a page uses an iframe or a pop-up or it makes a link navigation. A link navigation simply means that when you click a link or submit a form that opens a new tab, this tab will have a connection to the opener, and to simplify this implementation, they simply reuse the renderer. And in this case, again, even if the same origin policy of the browser ensures that a trusted site loading a malicious iframe should not worry because the iframe cannot access the contents of the trusted site, since they share the event loop, the malicious site can spy on the event loop and infer what the user is doing in the parent site. And this is the code, again, only 5 lines of JavaScript that we need to obtain an event delay trace for the event loop of the renderer. We have the same loop function. In the first, we save the timestamp, and now we will use the PostMessage API to post a message to ourselves, and then we simply define the loop function itself as a message receiver for these events. So we start posting a message, our function executes, we save the timestamp, and we post a new message, and so on. And with this technique, we get a resolution of less than 25 microseconds. Now, for giving you an idea of the relative duration of these events and what we can observe, in JavaScript, well, or in most web browsers, right now the Performance Now API restricts the resolution to around 5 microseconds, but usually events below this threshold are caused by microarchitectural events, and we will simply ignore them. And our baseline event will be our own task, the loop operation that takes around 25 microseconds. And here we have, for instance, the mouse movement. So every time that the user moves the mouse, this posts an event into into the event loop that will introduce a delay. So for mouse movements, we can see delays of 100 microseconds, which is 4 times larger than our baseline. So even the mouse movement is something really easy to spot in our event delay trace. Another example is the garbage collection rounds, which usually are very fast events, but take of the order of 1 millisecond. Another things are JavaScript functions for the event listeners, which take much more than 2 milliseconds. And the interesting thing here is that usually pages which has very short event listeners, or which are well coded and has a very responsive code, will have events much harder to identify. While pages with very inefficient event listeners will introduce very large delays that are very easy to spot in our event delay trace. And this is, we implement a tool called Lupus Candid that you can try if you like, where basically you can interactively observe the congestion of the event loops with the different techniques in real time. And we show some visualizations to zoom and export the files. So this is how we spy on the event loops. And now I will show you two of the 3 attacks that we implement. The first attack is a webpage identification attack. And the idea here is that given an event delay trace, we want to identify which page has caused this event delay trace. So in order to do this, we were looking for some distance measure between 2 traces, in a way that when the traces are from similar pages, the distance metric is, the traces will be close, and when the pages are very different, the traces will be separated. And in order to do that, we use dynamic time warping. So, for give you an idea of how dynamic time warping works, I will compare it with Euclidean distance. So, if we get the 2 traces, the naive approach is simply we apply the Euclidean distance, and this gives us some value of how similar they are. But the problem is that even when you load the same page twice, there are some delays in the events, probably caused by the network, that will make one of the traces to shift to the left or to the right. So at the end, you would end up comparing things that are completely unrelated. And the advantage of the dynamic time warping is that before calculating the real distance, what it does is it tries to find the optimal alignment between the 2 traces. And this intuitively is done by aligning the peaks of the trace. And it turns out that it works pretty well, and we only need 2 or 4 seconds of measuring a web page, which makes sense because usually loading a web page doesn't take more than that. And also we only need 1 trace for the training. And in order to evaluate the performance of this experiment, we use 500 pages from the Alexa Alexa Top 1000, I think. We pick 30 traces of each page. We tried in different machines in both loops. And what we did is prepare a reference database with 1 trace of each page. And then every time that we want to query a trace, we simply measure the dynamic time warping distance with all and choose the closest one. And with this simple approach, we got, in 75% of the cases, we were able to correctly identify the trace in the case of the event loop of the renderer. And in the case of the event loop of the host process, we could do that in 23% of the cases. The rates, however, are only for traces from the same machine. And when we try to evaluate the performance across machines, the recognition rate dropped quite a lot. And the intuition for why this happened is that, as I said, the dynamic time warping alignment works by trying to align the peaks in the 2 traces. And usually, if even the same event executing different machines will take more or less. So the absolute values of the peaks or of the delays will be different, and the dynamic time warping alignment will not work. But in any case, we have published the traces and the code for the experiments in this URL. And our second attack is the inter-keystroke timing attack. And what we try to do here is opening a pop-up page with a login page, and from the opener page, spy on the event loop and measure what happens when the user types its password. And this is like the visualization from the loop scan tool, and you can see a clear peak here when the user presses a key. So with this approach, we are not able to identify which specific key has been pressed, but we can obtain the password length and also the exact time between two consecutive pressed keys. And again, in order to evaluate this, we perform some more experiments, and for that we use Selenium to emulate a user. And what we did was the Selenium bot visit our page executing the spying code, click into the login button, which pop-ups the Google OAuth login page, and then it tries to log in by typing a random password with random delays between the two keys, between the two consecutive keys. And after that, it just submits the form. And with this, we repeat the experiment with 10,000 passwords, and in 90% of the cases, our page was capable of identifying all the keystrokes of the user. And the precision here is simply means that the difference between the real timestamp when the key was pressed and the timestamp that we have detected. And most of this noise is due to the Selenium. So if we remove Selenium and use a real user, this precision gets even better. So in general, this attack, we got more precision than previous network-based attacks. It's also less noisy than microarchitectural attacks, because usually in microarchitectural attacks, the resources or the cache, for instance, is shared among all the processes in the system, while here the event loop is only shared between the attacker and the victim. So the noise is much less. And also it does not require any privilege. We only need to execute JavaScript code, and we don't need any training at all. So since we know the pattern of the keystroke, and we have the event delay trace, we only need to traverse this event delay trace and extract the keystrokes. Okay, so now these were the attacks, and I will quickly discuss some possible countermeasures. The first one is reduce the clock resolution, which is well known to not work. I think that yesterday it was discussed also in some presentation, but in web browser there are simply too many ways to obtain a high resolution clock. So reducing the clock resolution of the Performance Now API will simply not work. The other alternative is, one very interesting approach from Google is the site isolation project, which has been developed by a few years now. I think that this year it has started to be shipped. And the idea of site isolation project is that to use the operating system to reinforce the origin policies of the browser. And what they are trying to do is that renderers should not be shared between pages from different origin. And if this ends up working, what will happen is that the render attack will not work anymore, because our malicious iframe will not be shared with a trusted site. But there are many more event loops in the browser, and the attack in the event loop of the host process will still work. Another interesting thing that Chrome shipped, I think, a few versions ago was the CPU throttling, which simply tries to restrict the time of CPU that a tab in the background can use. So basically, if we have a malicious tab in background, it will not be able to execute the monitoring code too often. However, this still doesn't stop the attack of the iframe, because when the iframe and the victim parent page are in the foreground, the iframe will be able to execute without the throttling. And also, with some of the techniques that we use for spying on the event loop of the host process, the CPU throttling doesn't work. The last countermeasure that we discussed, that it's probably the most interesting one, is that usually a vending page shouldn't be posting too many events per second. So maybe introducing some limitation into this posting, even if it can affect the performance, could be a good idea. And just as a summary, well, we have seen that the shared event loops in Chrome are vulnerable to side channel attacks, and we have systematically studied how this channel can be used for implementing different attacks. And while we are aware that this doesn't break the web, we believe that there exists a fundamental design issue in the event-driven architecture of the web browser that needs to be addressed. And that's it. Thank you for your attention.
Any questions?
Hi, David Kohlbrenner, UC San Diego. Great talk. So you talked almost exclusively about Chrome's event loops, and so Safari is obviously based on an earlier version of web. They split a while ago, and Firefox also has a notably different but similar style of shared event loops. Can you talk about how portable this attack strategy is to other browsers' shared event loop builds?
We haven't performed any exhaustive evaluation of other browsers. What we have done is trying a small proof of concept with the Lupus Candid tool in, I think, the nightly Firefox of a few weeks. And you can observe that there is some congestion. The problem is that I don't know the details of how the processes are separated and also how the event loops are shared. So probably the information that you can see is not exactly the same. But as you say, there are shared event loops used by all the browsers. And if you use the tool, you can see that, well, the delays are related to certain user actions.
Ben Stock from TISPA, interesting talk. I was wondering, probably you tried your attacks against having one tab open that loaded Amazon and Facebook, and then your attack tab, right? Does it make a difference if there's 12 tabs open? So is there, does it add background noise, which makes the measurements harder?
Yeah. Well, in the case of the renderer,
so basically 12 renderer processes. But so basically 10 of them are idle. One is the one where you load Amazon, and one is the one of the attacker. Do those 10 idle tabs, do they make a difference?
It depends. If they are, if one of them, for instance, does some kind of streaming, this is very noticeable in the input-output thread of the host process, because it will handle all the network requests and all the messages. But if the page is, well, at the beginning we had this problem with several pages, but with the CPU throttling, the background tabs can introduce some noise, but not too much, because they are precisely limited by this throttling. So if you have many tabs and they are doing some hard work, you will notice it. But normal tabs, usually when they have been completely loaded, are quite calm. Okay.
And if there's no other questions, I'll have another one. For the time warping, so assuming that this works with a kind of high bandwidth 100 megabits connection, and at home I have like 60 megabits maybe, I get that basically the whole thing is just stretched out. But if we consider that we're here and the Wi-Fi is not really working that well, so you have a lot of jitter in how long it takes, is it still possible to then identify pages, or does it really break it here?
We haven't done these experiments. When we tried, we simply tried with a normal network behavior, and it kind of worked. But I don't know if introducing some kind of noise would affect a lot this. I hope that because of the cache mechanism, probably the most important things will not be completely destroyed, but I cannot say.
Right, thanks.
Thank you.
Okay, I also forgot to mention at the beginning that this paper won a Distinguished Paper Award, so if you haven't been following along in your program, I just wanted to draw your attention to that, so congrats on the nice work, and let's thank Pepe again.
Thank you.